Okay, welcome back. Second talk of the morning session is Henning Samtleben talking about exceptional field theories and AdS compactifications.
Okay, so first of all, thanks a lot for the invitation to speak, to come to this great place and for putting together this very nice workshop. So I'll give a review of exceptional field theories, of the formalism of exceptional field theories, and then discuss a few applications of where we can put this to place and use it to solve some old problems in supergravity. So I'll do it in two parts. The first one is a bit more introductory. It's a review of this formalism of exceptional field theory, building on exceptional geometry, tensor hierarchy, constructing invariant action functionals, and then arriving at a duality covariant formulation of supergravity theories. So some of you know this very well already. Still, I think it's good to have a kind of pedagogical introduction to set up notation and all that. And then I come to the second part, which is applications of all this nice formalism to something concrete, to study AdS compactifications, and discussing how this is a very nice, very efficient tool to discuss consistent truncations. And then that is some very recent work, how it's also an extremely efficient tool to do Kaluza-Klein spectroscopy. So that's the really new part, which we are very excited about at the moment, that this turns out to be extremely powerful. This is mostly based on work with Olaf Hohm and Emanuel Malek, and then also on previous work with Baguet, Inverso, and Trigante. Okay, just a few words for the context, which probably is not is known to everybody. So all this is based on the duality symmetries of supergravity, which come from the duality symmetry of string theory. But in supergravity, we see them as we see the continuous versions of these exceptional duality groups showing up as global symmetries of maximal supergravity. As first observed by Kremer and Julia in '79, if you compactify 11-dimensional supergravity on a torus, you have 4-dimensional maximal supergravity, which comes with a global continuous E7 symmetry. And that holds true for all maximal supergravities. Say, if you compactify type 2b on a 5 torus, you have a 5-dimensional theory. It has a global version of, it has a global continuous E6 symmetry. But these symmetries, they only come about after you really properly decompose your fields, you reorganize them into new objects, dualize the degrees of freedom to the appropriate degree. Once you build the right objects, you find this E7 or this E6 symmetry realized. It doesn't come for free if you just do the reduction. And in some sense, the underlying theme of all this construction is the question, to which extent are at least remnants of these groups already present before you do the toroidal compactification? To which extent are they specific to the torus? To which extent is there some remnant already up in 10 or 11 dimensions? And that has triggered a huge body of work, bringing all these nice concepts of double field theory, generalized geometry, exceptional geometry, gauge supergravity, and all that comes together to build these exceptional field theories, which I'll describe. So I'll discuss in detail one example of an exceptional field theory for the exceptional group E6. You can do the very same construction for all the other exceptional groups. They all come a little different. Everyone has a little story on its own. E6 is a very characteristic example. It shares more or less all the typical properties of these theories, and it's one of the most compact ones. So I remind you, E6 is the symmetry of 5-dimensional supergravity. So it's what I get if I compactify 11-dimensional supergravity on a 6 torus to a 5-dimensional field theory. So let me just start putting out the first action. This is really 5-dimensional supergravity. This is a 5-dimensional field theory. It's a 5-dimensional action. It's what you obtain if you put 11-dimensional supergravity on a torus and reorganize your fields accordingly. So what you find is a very simple action. This is a 5-dimensional action. It has basically all the standard terms and nothing more. It was written down by Eugène Kremer in the 80s. So let me just go through the terms. There is a 5-dimensional metric. We are talking about 5-dimensional gravity. This is the standard Einstein-Hilbert term. These are the scalar fields. They form a sigma model. The sigma model is E6 over USP8. I write it in terms of a 27 by 27 matrix, which is parametrized by the scalar field of the theory in the standard fashion. So this is just a standard coset space sigma model. Next, there are 27 vector fields in the theory, and the 27 vector fields just come with a billion Maxwell field strength contracted precisely with that scalar matrix as is standard in supergravity. Okay. 27 is the fundamental representation of E6, so all these objects transform linearly actually under E6. E6 is manifest in this way of writing down the action. Vectors are just in the fundamental representation. Scalars transform non-linearly, but in this coset space, and so a term like this Maxwell term is manifestly invariant. And then the last term is a topological term, which you can have in 5 dimensions of the type F wedge A. To make it topological, we need to contract these 3 objects with a constant tensor, and the group E6 precisely has this totally symmetric constant D symbol, which enters thus here in the topological term. And that's it. That's the action after, of course, a lot of work, after taking the 11-dimensional fields, breaking them up, and putting them back together. So these vector fields, they would combine fields from the 11-dimensional metric, the 3 form, and so on, similar the scalar field matrix, and so on. Okay? But the result is an action which is manifestly E6 invariant. All this after reduction on the torus. So now the question is, what happens if we try to do exactly the same thing? We try to do exactly the same reorganization of fields. We break up the 11-dimensional fields. We mix them into new objects, which are these formerly E6 invariant objects. Okay? We do that very same procedure, but at no point do we drop the internal coordinates. So we stay all the way through with an 11-dimensional theory. Still, we try to build up these same objects as if we were doing a torus reduction to 5 dimensions. Okay? It's kind of similar in spirit to William's talk yesterday, breaking up 11-dimensional supergravity into the objects of a lower dimensional theory, but keeping all the way through the internal coordinate dependence. So if you do that, and you do exactly the same type of work, which is a little more messy, you come to an action which looks almost like the previous one. So this is what you find. Okay? We should go through the details. I mean, but you see structure-wise, this again is an action which looks very close to the action of 5-dimensional supergravity. Just all the objects have been slightly modified in a way I'll tell you. Okay? So we kept the dependence on internal coordinates. So all these objects now depend not only on the 5 coordinates of our 5-dimensional spacetime, they also depend still on the 6 internal coordinates, which we have not thrown away. Okay? So that's like if you do standard gravity and you do Kaluza-Klein theory, but you keep all the Kaluza-Klein towers. You don't restrict to the lowest modes. You would find a lower dimensional theory which has infinitely many fields, which are all the Kaluza-Klein towers. And then, as you know from gravity, this lower dimensional field theory, which has infinitely many fields, now features some infinite dimensional gauge symmetry, which corresponds precisely to the diffeomorphisms in your internal directions. So the internal diffeomorphisms show up as a local gauge symmetry in the lower dimensional theory. And since it's infinitely many fields, it's an infinite dimensional non-abelian gauge structure, which we have corresponding to the internal diffeomorphisms. Okay? So all that is very standard from standard Kaluza-Klein theory. The new ingredient here is that since we're dealing with supergravity, we also have to take care of the p-form gauge symmetries, and also we have to take care of that dualizing fields, say from 2 forms into vectors, from 3 form into scalars, which will add something to the story. Okay, so technically it's a bit more than just a standard Kaluza-Klein theory. So this is the non-abelian gauge structure which comes out from that. All local gauge symmetries combine into single gauge parameter, which takes values in that fundamental representation of E6, and it combines the internal diffeomorphisms, okay, which were a symmetry up in 11 dimensions, so they survive as a local symmetry in 5 dimensions. There are 6 of them. The internal 3-form gauge transformations from the 3-form of 11 dimensions, they bring in 15 additional gauge parameters. And then the internal 6-form gauge transformations, also from 11 dimensions, bring in another 6 gauge parameters. Okay? So altogether that makes a vector of gauge parameters, which precisely has this form of the fundamental, which precisely transforms in the fundamental representation of E6. And now this local gauge symmetry, triggered by such parameters, takes the form of what goes under the name of generalized diffeomorphisms. So on a vector, it would act by this following action. You see, it looks almost, if they were not for these brackets and the kappa, this would just be the standard diffeomorphism action, now on some kind of 27-dimensional space. Okay. Standard diffeomorphism action is not what can be the solution here, because we want an action which is compatible with that group E6. So for example, we want that this diffeomorphism action still leaves invariant the topological term, which carries a constant tensor of E6. Standard diffeomorphisms don't have any constant tensors. These diffeomorphisms are tailored such that they preserve E6, that they're compatible with the E6 group structure. And the way they do it is very straightforward. This second term of the diffeomorphism, which if you look at it, looks like a rotation with a diffeomorphism, with a derivative of the diffeomorphism parameter. This rotational matrix is projected onto the adjoint representation of E6. Okay, that's what the brackets do. And that's what makes this different from the standard diffeomorphism action. And that's what forces this action to be compatible with the E6 group structure. So for example, if you act by such a diffeomorphism, with this projection put in here, if you act with that on a group-valued matrix, such as our matrix up here, if I act on a group-valued matrix, it remains within the group, okay, which would not be true for a standard diffeomorphism action. Likewise, if I act with this type of diffeomorphism on, for example, this constant D symbol, it is invariant under this type of diffeomorphisms. It would not be under standard diffeomorphisms, of course. Okay? So that is the algebra structure, which comes from dimensional reduction and which can be cast into this very nice and compact form.
Sorry, can I just clarify?
Yes.
Is this a restriction on the space of possible diffeomorphisms, or you change the definition and
you change the definition of the diffeomorphism?
So it's
absolutely.
arbitrary,
It's not a.
not
You see,
normal.
you could also have tried to say, I want to make this compatible with E6, so I restrict to diffeomorphism such that this gradient matrix here is E6 valued. That would be a restriction on the internal diffeomorphisms. But that turns out not to be the right answer. Okay? You should, because in some sense, we know the theory should feature all these the theory should feature all these local symmetries, not just a subset. Okay? So the right answer turns out to be no restriction on this parameter. However, put by force or by brute force a projection into the action of the diffeomorphism. Okay? So exactly, I mean, it's a different thing than restricting the diffeomorphisms. Okay? And that's it. Okay, to write it in this E6 covariant form, we have sort of promoted derivative operators who used to live just on this internal 6-dimensional space into what looks formally like 27 coordinates. And to compensate for that, you have to impose what goes under the name of the section constraint. So particular quadratic combinations of derivatives when contracted with a D symbol, in fact, turn out to be 0. Okay, so that means whenever two derivatives hit the same object or different objects, but are contracted with a D symbol, this combination is supposed to be 0. And that's like a restriction on the coordinate dependence of all fields of the theory. And what that is, that looks always a bit mysterious, but what that is actually nothing but saying that out of these 27 formal coordinates you introduced, only 6 are actually alive. Only 6 are only physical, and that is the 11-dimensional theory. It's like a covariant way of restricting 27 coordinates down to 6. Okay, because written as an equation like that, it's nicely 6 covariant. Okay, and so there is a solution to this equation. There is a solution breaking these 27 formal coordinates under the GL6 subgroup, they go to 6 plus 15 plus 6. If you drop all these coordinates, you only have fields depend on the 6 first coordinates, then these equations turn out to be trivially satisfied. Okay, so they bring you back from that 27-dimensional structure to just a 6-dimensional physical space.
Sorry to interrupt again.
Yes.
So this is saying I'm compactifying on a torus at this stage. This last line, basically, you're saying that there's only dependence on 6 coordinates.
No, that's the internal coordinates. Right? I still have my 5 coordinates of AdS. These are the 6. I'm saying formally it looks like I introduced 27 internal coordinates instead of 6. Okay, but out of these 27, only 6 are alive. Those are the coordinates on which I formally threw away completely. But now I keep them, but I keep all 6 of them. So I still have all 11 coordinates. Okay? Turns out there's a second solution.
Can I ask one question? That's, suppose we think of this as a compactification of type 2 theory and not 11-dimensional supergravity.
Yes.
Could you have gotten the same result?
Exactly, that's what I'm about to say. Turns out there's a second solution to this section constraint in which you keep only 5 coordinates. The 5 not being a subset of these 6, breaking E6 in a different way under GL5 type SL2, composing coordinates like this, keeping those 5, and turns out that will be the type 2b theory. Okay? Whereas type 2a is just a subset, of course, in here for the compactification. But so there's an orthogonal, a complementary solution, independent of the first one, which in fact will bring us back to the type 2b theory. Okay? Now, this is a very nice, intriguing algebra here, due to the fact it's not standard diffeomorphisms, it has been projected. So obviously that changes all the discussion of closure of the algebra and so on. Turns out that the non-associative gauge algebra, okay, which in particular means if we want to set up a non-abelian gauge theory with it, and we will have to do because we have to generalize what used to be the Maxwell field strength to Young-Mills field strength, according to this non-abelian algebra. If you have a non-associative algebra, the standard Young-Mills field strength is no longer a covariant object, of course. So it turns out this field strength has to be modified by coupling to 2-form tensor fields.
Henning?
Yes?
When you say non-associative, you mean Jacobi identities? It's not a, right?
I mean, Jacobi identities are not satisfied.
Exactly.
Not satisfied, yes.
Thank you.
Okay, yeah, that's right. So it's an algebra which does not satisfy the Jacobi identities, which has a non-vanishing Jacobiator. But this non-vanishing Jacobiator has 0 action on all the fields, so there's no contradiction with the fact that this is supposed to become a symmetry of our theory. Okay, but as an algebra, it's non-associative. It's non-associative in the sense it does not satisfy the Jacobi identities.
Well, I mean, Lie algebras are non-associative. So I think Jacobi identities
depends how I
what you
define the
should
problem.
say.
Okay, that's terminal. Okay, but I think we know what we mean. Okay. So it's an algebra which does not satisfy the Jacobi identities. If Jacobi is not satisfied, Young-Mills field strengths are no longer covariant. You can turn them into covariant objects if you couple them to 2 forms, and to 2 forms under internal derivatives. So from the 5-dimensional point of view, this looks like a Young-Mills field strength, and that looks like a 2-form on which some internal derivative operator acts. So from the 5-dimensional point of view, this looks like some kind of Stückelberg coupling of a 2-form to a Young-Mills field strength. And if you do it properly, if you do it with precisely this form, 27 2-forms in the dual representation to the vector fields, coming under contraction with this derivative operator and the D symbol, that will precisely turn your field strength. And if you impose proper transformation rules for this 2-form, that will precisely turn this field strength into a covariant object. Okay? But you need new objects for that. You need 27 additional 2-forms. In 5 dimensions, that is very nice because there's precisely 27 vectors on-shell dual to 27 2-forms. So in principle, there's space for precisely these objects. But we have to introduce them as new objects to this Lagrangian. So this Young-Mills field strength here will now also carry this term here. Okay. These are new objects, but they don't add degrees of freedom. They don't come with a kinetic term. Instead, they also feature in the topological term. So the topological term is a non-abelian topological term. It used to be just A wedge F wedge F. Now I better write its differential to make, it's a non-abelian, so if I write it out explicitly, it's a mess. But if its differential, of course, is nice, its derivative. So it's f wedge f wedge f with now the full non-abelian f from here. But then also it has a term like this, h wedge dh, h being the field strength of these new objects, B. Okay, so that's basically the different topological terms you can write down in 5 dimensions, either an f cube or an h wedge h term from a two-form field strength. And that means if you, for example, look at the equations of motion, which these new fields now introduce, well, they will get a contribution from here and from the topological term, and that equation of motion will precisely be the duality relation between vectors and two forms in 5 dimensions. So these are new objects you have to add to make things covariant, but by their field equations, they will eliminate all the degrees of freedom. So I don't add anything new to the story. That's exactly how it works from what we know in gauged supergravities. You add extra fields to the theory, but they bring in their own first order equations of motion, and thereby sort of eliminate themselves their degrees of freedom. Okay? So it's still the same counting of degrees of freedom. So we have done these first 4 terms we have found now. So they are exactly as they were in the 5-dimensional theory, except now all equipped with this non-abelian gauge structure. So covariant derivatives here, taking care of this local symmetry. Young-Mills field strength here of this modified form. A topological term turned non-abelian, such as here. The Einstein-Hilbert term also gets slightly modified because the 5-dimensional metric, it doesn't have any E6. It's singlet under E6, but it carries a weight under these diffeomorphisms. So there's also non-trivial covariant derivatives in this Einstein-Hilbert term. And then the last term, which I haven't put, is this, what people often refer to as the potential of the theory. It's a term which collects all the 2 derivative terms with 2 internal derivatives. So from the 5-dimensional point of view, it doesn't have any derivatives. It looks like a potential for my fields. From that point of view of an internal geometry, this looks like a generalized curvature scalar, you could say, on this internal space. And turns out, this, even though this is not manifest, this combination of derivatives is invariant under generalized diffeomorphisms. Even though you only see partial derivatives, nothing covariant here, but that particular combination is invariant, such as is the Ricci scalar in GR. Okay, so it's like the analog of the internal curvature scalar. Now with all this together, the action is invariant under these generalized diffeomorphisms. It is almost unique. Okay, every term is uniquely turned into an invariant term by this covariantization. Turns out if you also impose diffeomorphisms in that 5-dimensional space, okay, each term is invariant by imposing the generalized diffeomorphisms on the internal space. If you also want to impose diffeomorphisms in the 5-dimensional space, in the standard 5-dimensional 5 coordinates, turns out that also will fix all these relative coefficients. Okay? So there's only a single combination of terms which is invariant under generalized diffeomorphisms in the internal and the external part together. Okay. And the coefficients which come out are precisely those which fit with 11-dimensional supergravity. So that's a Lagrangian which is uniquely, and we haven't made any reference here to supersymmetry. So that's a Lagrangian which is uniquely fixed only by the bosonic symmetries, however, which feature these generalized versions of internal and external diffeomorphisms. Okay? So that's a unique 2 derivative actions. We have not used supersymmetry. However, if you wish, you can add fermions to this theorem, make everything supersymmetric. There's a whole different structure yet behind that, which I will not discuss in this talk. So that is a kind of unique 2 derivative action you can write down, compatible with these symmetries. Modulo this section constrained, which, as we were discussing, has 2 inequivalent solutions, either retaining 6 or retaining 5 coordinates. And depending on which one you choose, and applying the proper dictionary of these fields back to the high-dimensional origin, the equations of motion of this Lagrangian will precisely reproduce the full 11-dimensional equations of motion, or the full type 2b equations of motion, depending simply on how you put the section in this 27-dimensional set of coordinates. Okay. You have to properly translate your field. So for example, if this is this 27 by 27 matrix, if you want the 11-dimensional origin, well, you have to block decompose it. You will find here some blocks which carry, for example, here the internal components of the 3 form, piece of the 6 form. Whereas if you decompose on a type 2b, you will here find the dilaton axion matrix. You will find here the 3 forms from type 2b and so on. Okay? So if you do the proper field decomposition, plus you apply the right choice of coordinates, then this one kind of master action either is full 11-dimensional supergravity or it's full type 2b supergravity. Okay, so the picture is like this. We have a dictionary of this, depending on how we parameterize our fields, either into 11-dimensional supergravity or into type 2b supergravity. So that's the formalism of exceptional field theories. That is for the group E6, but you could do the same for E7, E8, SO55, SL5. Always the structure of the action will really mimic the one of the supergravity in the corresponding dimension, except for all fields are promoted to depend on all internal coordinates, and you supply things with these covariants under generalized diffeomorphisms. That's the recipe. Okay? So that's a very nice formalism, especially because you have kind of a master form of equations of motion, which you can either turn into type 2a or type 2b equations of motion. Let me discuss now some very neat applications where you can put this to use to actually, I mean, it's one thing to have a nice formulation of the equation of motion. It's even better if that can serve to solve something which we couldn't solve in the old formulation. So let me review one nice construction, which is the consistent truncations of supergravity on spheres. Okay, that's like a classic problem in supergravity, which goes back to the 80s. Again, let's pick one example which fits with the previous discussion. That would be the AdS5 times S5 background of type 2b. Okay. So that's a fully supersymmetric solution of type 2b. People have worked out the Kaluza-Klein towers of fluctuations around this background. That was already done back in the 80s. And it turns out the lowest Kaluza-Klein multiplet around this background precisely carries the field content of 5-dimensional maximal supergravity of its gauged version, in which an SO6 subgroup of E6 is gauged. Okay? So the lowest multiplet precisely coincides in field content with maximal supergravity, and so that triggered the long-standing conjecture that in fact maybe the full nonlinear maximal gauged supergravity could have an uplift into the type 2b theory. A consistent uplift, a nonlinear embedding into type 2b, such that any solution you find to the 5-dimensional equations of motion in fact defines a solution of the type 2b equations of motion. That's the issue of consistent truncations. The field equation of type 2b with a particular reduction ansatz reduced to the field equations of this 5-dimensional maximal supergravity. And if that is true, that is a very powerful tool to compute solutions, do calculations in type 2b just with a 5-dimensional Lagrangian. And some parts of these nonlinear uplift formulas are known and standard in Kaluza-Klein theory. So the metric, for example, would be given in terms of the killing vectors on that sphere, some 5-dimensional fields. The internal block of the metric, again, would carry all the 5-dimensional scalar fields contracting the killing vectors on the sphere, and so on. But the difficult part is to extend this to all the p-form fields of type 2b. And that for a long time, only very few examples of such consistent truncations were known. Okay? As I said, they are a very powerful tool, for example, for constructing solutions. They are very useful if you want to do holography with that, if you want to do AdS CFT, and you want to know to which extent you can trust any computation, say of holographic correlation functions, which you have obtained by a 5-dimensional supergravity calculation. You should trust only those which you can consistently embed into the type 2b theory. They used to be very rare. In fact, in the 80s, 90s, only very few examples of such consistent truncations other than tori were known. So the first example fully worked out was the S7 reduction of 11-dimensional supergravity by David and Nicolai in 87. And then like 12 years later, Nastas van Nieuwenhuizen and Warman did the AdS 7 times S4. And only with this modern technology, which I want to describe now, this has kind of exploded. So nowadays there are consistent truncations everywhere. Turns out to be a very generic property of supergravities, and in particular this AdS 5 times S5, which we need a lot in the AdS CFT correspondence, turns out to be also on the list of consistent truncations. Okay. And that is because in this framework, or in these new variables of exceptional field theory, the problem, in fact, has a very simple solution, extremely neat, which also has a long story which came in generalized geometry and double field theory, and then finally also applies to the exceptional framework. And it goes like follows. What looks like a very complicated reduction here on a sphere. In fact, once you translate it back by the dictionary into these new variables, which are already tailored to talk to the 5-dimensional supergravity, in terms of these new objects, in fact, that looks like a Shirk-Schwarz reduction on a twisted torus. If you make it more explicit, it's like standard Shirk-Schwarz reductions in gravity. So in terms of these objects, for example, this M E6 valued matrix of scalar fields, the reduction ansatz is a simple product formula. Okay? So the basic ingredient is what we call a twist matrix, U. That's an E6 valued matrix. Okay? It lives on the group E6, and some scale factor which takes care of some weights. But so essentially what happens is this E6 matrix of exceptional field theory, which I remind you contains all 10 coordinates. That's an object of the type 2B theory in disguise. Takes the following form. It factors into this twist matrix, which takes care of all the sphere dependence, of all the dependence on the sphere coordinates, and they are just sandwiching the 5-dimensional matrix of 5-dimensional scalar fields. Okay? So in terms of these objects, reduction looks extremely simple. It's just a factorization ansatz. Same holds for the vector fields. They just get the twist matrix multiplying the 5-dimensional vector fields. The two forms just get the twist matrix, it's inverse actually, multiplying the 5-dimensional two forms, and so on. Okay. So in terms of the objects up here, all you have to find is the twist matrix relating to the 5 sphere. And the twist matrix, that is as in Shirk-Schwarz, you cannot choose it arbitrarily, of course. It has to satisfy a certain amount of consistency equations. They take this form of first-order differential equation on internal space relating this particular combination to the structure constants of 5-dimensional supergravity. Okay? So if you remember Shirk-Schwarz reductions, that is very reminiscent of the equations you impose in Shirk-Schwarz reductions, except for now these groups are, these matrices are group valued in E6, and you have to put a particular projection onto a particular sub-representation of E6, the 351. That's the only input, the only extra input, as opposed to standard Shirk-Schwarz. And the mathematical structure behind is that of a general or Leibniz parallelizability of these U matrices as frame fields with the structure constants of 5-dimensional supergravity. In standard Shirk-Schwarz, you may remember this looks almost the same, except there's no projection. You antisymmetrize, and you have here the structure constants, the standard structure constants of supergravity. In that case, because these will be structure constants of a Lie algebra, you know even how to integrate up these equations. And you integrate them up into group manifolds. And so standard Shirk-Schwarz reductions go in one-to-one correspondence with group manifolds. Here everything is slightly modified. In particular, as we discussed already, here typically what shows up is non-associative or non-Jacobi identity-satisfying algebras. So these, in fact, are the structure constants of the Leibniz algebra, not the Lie algebra. So it's far less clear how to integrate up these equations in a general fashion. Okay? But we can find solutions to this on a case-by-case basis to start with. So for example, the twist matrix corresponding to the 5 sphere is very simple. It is a particular SL6 matrix, 6x6 matrix, which you can easily express in terms of the sphere harmonics, the elementary sphere harmonics on the 5 sphere. Okay, so these Y fields would be the elementary sphere harmonics on the sphere. That's a 6x6 matrix, and since SL6 embeds into E6, you can easily embed this into a big E6 matrix. And as a big E6 matrix, it can act on these fields. Okay, and that's it. Once you have, it's easy to check that this satisfies the consistency equations. It's like a 3-line computation to show that these, in fact, now provide a consistent truncation of this theory up here.
Is it clear that for every such Leibniz algebra that rule can be integrated, at least in
No. No, quite the opposite. We know that there are some where it cannot be integrated.
I'm sorry, just to comment, these Leibniz algebras that appear there, they're always actually weakly 2 algebras in disguise. So you can, there's an abstract integration theory for that. So you can integrate them in principle, right? The formulas will get ugly.
Okay, depends on what you, depends on what you have in mind. You see, it's differential equations, but in this internal space. So the formal derivative in 27 dimensions, okay? If we want something which corresponds to 11-dimensional type to be supergravity, we have to keep in mind we have to impose a section constraint on that. So in fact, we should not allow a full 27-dimensional coordinate dependence. We should only allow for 6 or 5-dimensional coordinate dependence, okay? If you do that, then it's easy to show there are counterexamples where you cannot integrate it up just using those 5 or 6 physical coordinates. But where you would also have to span into the range of non-physical coordinates. And then, strictly speaking, we don't really know what we are doing because if the section constraint is violated, our initial formulation was not really a consistent one to begin with.
Is it violated locally?
Locally already, absolutely.
Another question.
That's the case, for example, for the omega deformations of 4-dimensional supergravity. It's easy to see for the omega deformations, this system cannot have a solution if you only allow for the physical coordinates.
When you construct action from that Lagrangian, what do you integrate over?
Okay. The safest thing is to do it on the level of the equation of motion. Okay. What you integrate over is kind of a subtle thing. I mean, the most honest way to think about that is to say you first solve the section constraint and then you integrate over whatever you have. And then you're back to 11-dimensional type 2B supergravity. Okay. For all these applications I'm discussing, that's exactly what you need to do. Okay. Now, you could write a formal integral over this space, but then, okay, then you touch upon many, many subtleties, which I have nothing to say about at the moment. Okay. Good. So that's just to say, this is a very nice and simple twist matrix, which brings, if you put it back here, if you lift this to E6, which is straightforward, it gives you these formulas. It looks very simple up here, but now you have to pull it through the dictionary to see what it actually does to your type 2B fields. The dictionary is kind of lengthy and complicated because you have to do this breaking, Kaluza-Klein style breaking, dualizing, and so on, but you can do it. It's unique. It's a unique dictionary. It holds for all compactifications. So once you've done the work, that's good. And this is what then, for example, the S5 reduction looks like in terms of the original type 2B fields. So that's the metric that's more or less standard. But here's, for example, it's not even the full formulas, but this is the 4-form. You see, these are the different components of the 4-form, depending on how many legs are internal or external. And they are all triggered by the 5-dimensional fields, 5-dimensional vector fields, 5-dimensional scalars sitting somewhere here, for example, and then multiplying particular polynomials in the sphere harmonics of the 5 sphere. Okay, so that's a very messy ansatz if you were to check, but the statement now is proven indirectly by this reformulation that if you plug this into the type 2B field equations, all the internal coordinate dependence will factor out and you will just be left with the equations of motion of 5-dimensional supergravity. If you tried with these with explicit expressions, that's a mess. We did it for some components where you can explicitly see it. You quickly run out of power because you need lots of identities relating identities between S5 harmonics to identities on the E6 structure of your 5-dimensional fields. But turns out if you do it, if you show it in closed form, in fact, it's a very simple calculation, and that shows the consistency of this reduction ansatz of the type 2B theory. So that is now the embedding, the full nonlinear embedding of 5-dimensional gauge supergravity into the type 2B supergravity. Okay, let me sketch 2 more applications which I find nice. Once you've done the sphere, you can do some simple modification to get other spaces. For example, you can take the twist matrix, which is not based on the sphere, but on the hyperboloid. So built from sphere harmonics on this coset space, SOPQ divided by SOPQ minus 1. Formally it looks exactly the same, just you have a different metric to compute these sphere harmonics. If you do that, from the point of view of these variables, things don't really change a lot. You get different compactifications now of this, and they bring you to different 5-dimensional theories, which may have compact gauge group SO6, non-compact gauge group SOPQ, or non-semi-simple even, like a CSO PQR subgroup in 5 dimensions. Okay? So here they look all extremely similar, but we can still pull this to the dictionary, to the type 2B theory, where they all now, after you do this translation, correspond to very different manifolds on which you compactify in terms of, from the point of view of this type 2B theory. So spheres, as we had seen, but then here would be hyperboloids, here would be some kind of warped hyperboloids with some flat directions. So particular configurations in this 5-dimensional internal space. Okay. That is based on some old work by Chris Hull and Nick Warner, who had these backgrounds identified already in the type 2B theory, and they match with the maximal supergravities in 5 dimensions. Here what we have now is really the full nonlinear embedding even of all these theories into the type 2B theory. Okay. One thing which is important to stress is these backgrounds in general are not backgrounds. These are not solutions. These are not solutions of the type 2B field equations. Okay? But they don't have to be in order to have a consistent truncation. Consistent truncation just means my 10-dimensional equations of motion reduced to 5-dimensional equations of motion. They don't tell me there is a solution around which I have to do that as a concept of the consistent truncation. I can still embed this full theory up in 10 dimensions. Same here, even if the background, which I shouldn't call a background, around which I do that is not a solution of type 2B. And that can be very nice. For example, I'll give you one example where you have a very nice application of that. That's even slightly more general. You can also extend this to product manifolds in certain context. Okay? This structure of generalized parallelizability in general is not inherited by products. So spheres, product of spheres and hyperboloids in general do not allow consistent compactifications. But there's an exception if you go down to 4 dimensions, and that's related to electric-magnetic duality in 4 dimensions. So I haven't talked about this E7 exceptional field theory. It looks very similar. It's like a cousin of the E6 one, but now coordinates live in this 56-dimensional representation of E7. And E7 is a subgroup of a big symplectic group. So these 56 coordinates you can split in some particular symplectic frame into something like electric and magnetic coordinates. And it turns out a compactification on such a product can be made consistent if you use electric coordinates for one space and magnetic coordinates for the other. But you have to do it in a way that the section constraint is still satisfied. So we are still talking about 11-dimensional or type 2B supergravity. It's just disguised because we have done a symplectic rotation on all of that. Okay? And we have put one space in the electric half and the other space in the magnetic half. And depending on how you split your coordinates, you may describe compactifications on all these spaces, on all these product spaces. And one which is a nice example, which illustrates a bit what I wanted to say before, is this choice, 5+1 split of the 6 coordinates. Okay? So you have an AdS4 times S5 times, that would just be the real line here, a consistent truncation of the type 2B theory. Now that's, of course, that's not a solution of type 2B, as you know. Okay, so this is not the background. Still, the claim is there's a consistent truncation around this to a 4-dimensional maximal supergravity, and that is one of these called dionic gauged supergravities, which have funny gauge groups SO6 times SO11, semi-direct product with a bunch of translations. And those are interesting theories because it turns out they are dionic, they feature electric and magnetic vector fields. They have very interesting vacuum structure in their scalar potentials. For example, this particular solution, okay, that corresponds to a point in the scalar potential which is not a stationary point. And that's just reflecting the fact that this is not the solution of type 2B. This is not the solution of type 2B, so the 4-dimensional solution where I put my scalar fields here, all to 0, is not the solution either. They will run. But they can run now. I have a 4-dimensional theory. They could, for example, run into this vacuum. Here they are stable. Okay, that's a 4-dimensional stationary point of the extrema, of the stationary point of the potential. Okay, but this theory has a full nonlinear embedding, consistent embedding into type 2b. So this point also has an uplift into type 2b. In 4 dimensions, this is an n equals 4 vacuum which has half maximal, SO4 remaining symmetry. Okay, by this consistent truncation, it has an uplift into the type 2b theory. Now scalars are excited here. Scalars have non-vanishing expectation values, so that means this geometry here has been deformed up in type 2b, and you can pull it through the dictionary, and you find that things turn into a geometry which looks more like fibered S2 times some Riemann surface. Okay. And that's a solution which already showed up before in the classification of half PPS solutions in type 2b by these people. But now we have that solution within a particular consistent truncation down in 4 dimensions. How long do I have?
15.
Very good. Okay, so that's another neat example which shows you that in principle, even if you have a consistent truncation around something which is not a background, that can still be very interesting, because in that very same theory you might find other extrema. Now you can go on the search in this potential, find different solutions, and they will all allow for uplifts to type 2b. Okay, now let me do the last part. That's the most recent thing where we can even extend these consistent truncations to something more powerful, which is really doing Kaluza-Klein spectroscopy around these vacua. So that's recent work with Emanuel Malek. So let me just say what this is about. So we have been discussing the compactification on AdS 5 times S5. We have seen the lowest Kaluza-Klein multiplet, in fact, corresponds to 5-dimensional gauged supergravity. That's now the story we can build on. But then remember, there's of course all the Kaluza-Klein towers of linearized fluctuations around this background. And those masses of these Kaluza-Klein tower, they have been computed in the 80s by, for example, Kim, Romans, van Nieuwenhuizen. They give rise to tables like this, infinite series of scalar fields in increasing representations of SO6, building the infinite spectrum of the theory, of the type 2b theory around this point. Okay. Now we know the lowest multiplet has this very nice embedding into our new formulation, into our new variables. Okay? So it's very natural to ask the question, where are all the other Kaluza-Klein modes sitting in this new formulation? Okay. In terms of these objects here, these exceptional field theory objects, that is supposed to be the full type 2b theory. So in particular, it should carry the fluctuations. So how can we make them, how can we identify them? So let me just remind you how you do that in the standard formulation. Okay. Traditionally, how do you compute a Kaluza-Klein spectrum? Well, you should do some kind of harmonic analysis on the internal space. But here it's much simpler because the internal space is a sphere. It's a maximally symmetric space. So in fact, most of that is done by group theory for you. So for example, take a 10-dimensional scalar. A 10-dimensional scalar, you should just expand it into the sphere harmonics on the space. Okay? And the sphere harmonics for a sphere are just built by sort of traceless polynomials in the elementary sphere harmonics. And so they're labeled by the vector representation of SO6. Okay, so a scalar just has this tower of SO6 fully symmetric vector representations. If you do it for a different object, it can be more for example, this would be the internal metric. The internal metric has slightly more complicated structure because it carries sort of non-trivial Lorentz indices on the 5 sphere. So if you do that same kind of argument, you will find on top of that internal block of the metric sit 3 different Kaluza-Klein towers. Some coming with these vector representations, some coming with these different harmonics, and the third tower coming with these harmonics, which you can also all build in terms of these objects and their derivatives. Okay. So in terms of the metric, there's like 3 towers. You have to go through all the list of your type 2b fields, expand them according to that prescription into Kaluza-Klein towers. And then you have to plug that into the field equations, linearize them, and diagonalize them. Because, for example, you see here come fields with the sphere harmonic in these vector representations. They will necessarily talk to the scalar fields coming from that very same harmonic. So the equations of motion up type 2b will mix all these fields. So that's a big task, which was done by these people very bravely, putting an ansatz like this for all the type 2b fields in the fields, linearize the field equations, diagonalize this huge system, and from those mass matrices, well, obtain the real mass eigenstates, make tables with that, and then you can list them into some nice pictures like that. And the last task you should still do, if you go that way, we know it's a fully supersymmetric solution. These fluctuations should organize in supermultiplets. For example, this was the lowest BPS supermultiplet here. So you should now still scan through these fields and see how they fit together in BPS multiplets. So this would be the next one. This is the second. This is the third BPS multiplet, and so on. Turns out they fit. They have to fit, but you still have to go around and look how these fluctuations go together in multiplets. So this would be a given multiplet. Okay. So you can get there, but it's a lot of work. It's a lot of work to do it. Let's see how we can do that in our variables. So again, the lowest multiplet just had this nice factorization ansatz. Okay, this would just be the fields of the 5-dimensional multiplet. Now let's extend it to the higher Kaluza-Klein modes, and we'll do very simple. We'll just take this former ansatz, and instead of the 5-dimensional field, we multiply all this with a scalar tower of fluctuations. And this is just a scalar tower. It's just a single tower. It's not all the rest will be taken care of by this prefactor, which came from the lowest Kaluza-Klein multiplet and which we knew exactly. Okay. And if you do that, so you put just a simple sum of fluctuations in here with simply the scalar tower, it turns out this will reproduce the full Kaluza-Klein spectrum. Okay. It combines the ansatz for the lowest multiplet with the tower of scalar fluctuations. If you plug that into the field equations, turns out this is already the right basis in which all the field equations are in fact diagonal. So you are no longer obliged to diagonalize the big system of mixed equations of motion. You can zoom in on any single of these fields and you will already hit a mass eigenstate of 5 dimensions.
Can that fact be traced to supersymmetry?
Say again?
Can that fact be traced to supersymmetry? Like,
can you trace the supersymmetry?
Can that fact that this is already the correct basis for everybody,
yes,
can that be traced back to supersymmetry?
Oh, it's more general, I would say, because we will see examples where we have no supersymmetry at all, and it will yet be the right basis. Okay. So, as concerns supersymmetry, in this case it's indeed kind of related, because for fixed harmonics which I multiply everywhere, turns out those fluctuations precisely make up the full BPS multiplet. Okay? So in this basis, the BPS multiplets come horizontal. Fluctuation, I multiply one scalar fluctuation and they come already horizontal BPS multiplet. You don't have to diagonalize, pick up states and so on. Okay? It's very useful because if you have a given state now in the BPS multiplet, by going through that dictionary, it tells you immediately how does it sit in the type 2b theory. And that's what you want to know if you do holography or something. You have some particular operator, you want to see how does it sit up in the type 2b theory. Well, here it is. You just plug it into that. You're already diagonal. You plug it in here and you go through the dictionary, and that's it. Okay? It's a very simple, nice, compact rederivation of the supergravity spectrum and allows a direct identification of the BPS multiplets. Okay, that's very nice already. We can do the S5 result in much more compact form. We understand it better. But in fact, we can do even much better than that. So let me just finish with that. We can do much more interesting stuff with that, because think back about this ansatz. This was coming from the lowest Kaluza-Klein multiplet and then the fluctuations. Okay? But we have some extra bonus. We know in the lowest Kaluza-Klein multiplet, this ansatz is exact. It's a consistent nonlinear truncation to the Kaluza-Klein multiplet. Okay? What does it mean? It means in particular we could switch on non-vanishing expectation values in the lowest Kaluza-Klein multiplet. So here's an example again. That would be the S5 reduction. It brings you down to scalar potential. It's a scalar potential by Gunaydin, Romans-Warner 5-dimensional theory. It has a ground state, so this is the state, it's a stationary point. It corresponds to the round S5 sphere. But then again, in this potential, there are other points. For example, this famous Friedman-Gupta-Pilch-Warner flow, holographic RG flow, which brings you from this point to a different stationary point. Okay? Here, supersymmetry is broken to 1/4. That should correspond to some very much deformed 5 sphere. It only has U2 isometries left. We know, of course, how to uplift this. We can do this by the technology we have introduced. Now, what we are saying is, if I go to this point here, by applying that very same formula, I can even derive the full Kaluza-Klein spectrum at this point. Okay, the full type 2b Kaluza-Klein spectrum around this geometry. This geometry is some kind of ugly thing, very much deformed sphere, which is not even a symmetric space. Okay, but this formula here gives you the full Kaluza-Klein spectrum, all the infinite Kaluza-Klein towers now around this geometry. Okay, what you could do with the standard technology was, of course, the spectrum has been computed within 5-dimensional supergravity, but that will only account for the 128 degrees of freedom of 5-dimensional supergravity of the lowest Kaluza-Klein multiplet. So those masses we know. We know how the lowest Kaluza-Klein multiplet splits into n equals 2 multiplets that we can compute in supergravity. But now we can do the very same for all the infinite tower of Kaluza-Klein multiplets. If you wanted to do that the type 2b way, well, you would have to do harmonic analysis on this non-symmetric space corresponding to that deformed geometry. You would have to take account the effect of the non-vanishing p-form fluxes which you have switched on and so on. So good luck. That looks extremely hard to do. I don't even know if it's possible. Here it comes out for free. You plug this ansatz in, and this is a nice mass formula, which here just one example. That's the mass formula for vector fields. Okay, very nice formula. It only carries the structure constant of 5-dimensional supergravity of the lowest dimensional multiplet. So these x's are the ones of the Guinaidian-Romans-Warner theory. And it does some bilinear combination with these are the constant matrices of the action on sphere harmonics. So this is some SO6 representation. You just work out this thing, and that gives you the full mass spectrum. Okay, so similar here for the scalar fields. It's a bit more complicated, but still it's a closed formula. It applies for all compactifications. Okay, and in every case, it will bring you the full Kaluza-Klein spectrum. So here, for example, that's the Kaluza-Klein spectrum at the first level, which you can compute. It fits. It falls nicely into BPS multiplets as it should. It has some semi-short. Semi-short are not so hard to get because, in principle, their masses are known for determined by supersymmetry. But it also will bring you these long and very long multiplets with kind of very weird irrational masses. You can compute all of them now just within these data of 5-dimensional supergravity. Okay, there's a whole list of other vacua which would be very interesting to study with these methods. N equals 2, N equals 3. There's a potentially stable N equals 0 vacuum, which now we can really test, is it stable or not to the higher Kaluza-Klein modes. And maybe just one remark, since we have a session tomorrow after tomorrow on machine learning, there's a numerical scan by some research team at Google, which recently appeared to scan all the potential of 4-dimensional supergravity and find zillions of extremal points in there, most of them with no supersymmetry. We can, in principle, scan all this for the spectra and for the geometries which come with it. Okay, so I'll stop there. So it was just to illustrate this formalism of exceptional field theories and how we can use it as a very powerful tool for consistent truncation, constructing vacua, but also to study the Kaluza-Klein spectra around such vacua. And maybe to come back to the context of this conference in particular, the challenges of that program, one big thing would be if we could really include, if you could go beyond the two-derivative story here, include higher order corrections, see to which extent they might be constrained by such a purely bosonic analysis, decrease the number of external dimensions to come to larger and larger exceptional groups to make the picture more and more unifying, and then maybe understand at least better the nature of what are these section constraints and to which extent they are really necessary for the theory. And so it boils down to the question, is this just a nice new formulation? Is this just a nice new set of variables for supergravity theories in which we can solve some problems which we couldn't solve before? Or, again, the spirit of this conference, are these nice new variables also thereby some hint to the more fundamental structure behind all that? So I'll stop here. Thank you very much.
Any questions?
My question is about going beyond E8. Would any of this can be sensibly made sense of in a sense of writing down covariant Lagrangians?
Right.
E9 and beyond.
Okay. So the current status, I would say, is E8 is done. So all the finite dimensional groups fit in this framework. E9 is done to a large extent. E9 is the first group where you hit an infinite dimensional group. Because in 2 dimensions you have these affine symmetries in supergravity. So what you have to do is set up a similar Lagrangian, but now starting from an infinite set of fields, starting from an infinite set of coordinates onto which the the section constraint will only project onto finite subset. So we know what is the structure of generalized diffeomorphisms. That's work we did with Martin and others. We know, say, 3/4 of the action. We know the scalar potential in particular. So that will be under control. That's basically technical. For E10, and then the last step would be E11, or even the structure beyond E11. I think the most advanced result is this. My boss Kleinschmidt and Sesgin, who do a construction for E11, which has all the right features kinematically, which does not yet have the full set of equations of motion. Okay, but that is the spirit. I think that is the spirit in which to which this should lead. But then, of course, as you can imagine, it gets more and more complicated because you've it gets more and more complicated, but also, of course, it gets more and more unified because you give up more and more on this external space. So in the very end, there will be nothing but a huge internal space. So that, in some sense, should be the most satisfying one, but it will also be the most complicated one.
Any other questions, Chris?
Yeah, so my question is about the applicability, or how generally applicable, or to what backgrounds the exceptional field theory is applicable. So you started off by thinking about toroidal compactification, which has an E6 duality. Then rather interestingly, it extends to cases where you have some sort of twisted torus structure locally, in which case you have a formal action of E6, and then you find that the structure continues. There's other kinds of spaces where the duality story is very different. So, for example, if you take K3 cross a torus, you find a duality group O521, which doesn't fit inside E6, and so presumably that can't be readily thought about in terms of the E6 exceptional field theory. Instead, there's an O521 sort of doubled field theory, which you could use to talk about that. So it seems that there's each of those two different formalisms would talk about different classes of backgrounds, and then there would be yet other extended theories which would describe other theories with other backgrounds with other duality groups. And for backgrounds with no duality symmetry and nothing to do with the twisted torus, as far as I can see, we've still got very little idea about what the other degrees of freedom should be. So I wanted to hear what your reaction to that story is.
Yeah. What I should say is, of course, I mean, the class of consistent truncations I was discussing here is only those consistent truncations which bring you down to a maximally supersymmetric theory. And so they are built by these precisely twisted structures and so on, but they remain, they keep the same field content as what we had up in 10 or 11 dimensions. Okay.
Yeah, but for example, in the non-compact gaugings, you break the supersymmetry down to very little or nothing.
No. I mean, the lower dimensional theory is still maximally symmetric. The vacuum breaks it, you mean?
Yeah.
The vacuum breaks it,
it's the same
but as a lower dimensional field theory, it's still a fully maximally symmetric supergravity.
Yeah, but that's the same with the K3. I mean, it's still 11-dimensional supergravity on a particular background, so it still has 32 local supersymmetries. But the background breaks the supersymmetry.
Exactly. Okay, what I was going to say is, in this framework of the generalized Sturck-Schwarz reduction, as I presented, that fits precisely those theories which allow for a reduction onto something which is a fully supersymmetric theory, even though the background may break it. Okay. But that can be generalized. Emanuel Marlake has a very nice formulation of that, where you can also embed into this consistent truncations which bring you down to half-maximal theories, for example. Okay, and yet they fit into that, within that exceptional structure of the exceptional field theory, you can embed all the ingredients of a half-maximal supergravity in low dimensions, precisely to describe cases as K3, for example, in which all those data also fit into this framework. But in that case, of course, it goes more subtle. It doesn't go by like only twist. In that case, you don't have like an E6 twist matrix. In this case, that analog of the twist matrix is something which interpolates between those data and the data of a half-maximal supergravity. So I would expect that you can probably even push that forward even to cases with lower supersymmetry, but it gets more and more. It gets less and less I mean, this is the most compact formulation because this twist object is really like a group valued matrix. Okay? In the other cases, I need more like a thing which intertwines between these data and the data of a half maximal supergravity. And those are half maximal supergravities which I could not describe by double field theory, because those are cases where the half maximal supergravity cannot be embedded into type 2.1, but only in the type 2b theory. So some of the Raman fields are, some of the type 2 fields are excited, okay? They fit into this framework, but they will not fit into a DFT reduction of all that. So it's really, you need to embed the half maximal supergravity into the full exceptional structure. That's what I want to say.
Any other questions? Yes.
Yeah, possibly a partial answer to your last challenge. So in double field theory, at least, you see that the section constraint is sufficient for guaranteeing that on the big space, the generalized diffeomorphism for actually a higher Lie algebra. But they are not necessary, so you can weaken them. And I think the weakenings that are in the literature are precisely those that still lead to a higher Lie algebra. So you would expect the same here, I guess, right?
Okay.
So,
okay, yeah, there are certainly, yeah, there are many, yeah.
Any other questions? Yeah.
Is the fermionic part also studied? I mean, all the completed structures is studied also?
Yes, yes, okay. Yes. Yeah, I was just talking about the bosons because that already gives you the story. You can set up all that also for the fermionic part, okay? And then, okay, you will have to introduce a few more geometric objects because you need kind of a generalized spin connection on the fermion fields, which will look like again, it will look like the objects which you have already in 5 or in 4 dimensions, except for you will promote everything to full coordinate dependence. And you will have to introduce some geometric data on this internal space. But you can do all that for the fermions. You can check that the whole thing is supersymmetric. Okay? The main message here is the bosonic sector already fixes itself only by its symmetries. But then you can supersymmetrize it on top of that. Okay? But you don't need supersymmetry to fix the coefficients in the first place. But the fermions are studied. Yeah, we could probably also, we haven't done it, but we could probably also work out the fermionic Kaluza-Klein spectrum and all that.
Any further questions? Okay, in that case, let's thank Henning again.